cyclopentane or something, and then you have like two attachments, two substituents, I understand that each different, where you place it's a different isomer. But do you include the cis and trans and the regular ones without cis and trans, or?
Right.
Yeah.
So let's do an easier example of that. And that easier maybe example of that is how many, the pens go away for the weekend and they don't write on Monday. They really just don't. How many possible dichloral cyclopentanes? So how many possible dichlorocyclopentanes are there? I never feel like the English makes sense in here. So again, you know, when a question like this is presented to you, I mean, I'm sure this could be, this will be like a multiple choice question. And so I think that it's really, really important that you start out thinking, what exactly does that mean? And your cyclopentane is this, and how many places can you put the chloros, and be different, right? How many places, right?
3.
So you can put them on 1,1, so you can go ahead and begin on 1,1, and then you can come over here and go on 1,2, and then you can come over here and go on 1,3, right? And these are your constitutional isomers, right? So these will be the constitutional isomers. So I kind of go by, you know, what the multiple choice choices are. I mean, if we have 0, 1, 2, 3, none of the above, of course you're gonna go with 3, right? Does everybody follow? So you kind of are putting the lead. In reality, the question is going beyond that. Because when you have the 1, 2, the 1, 2 can really be your cis 1, 2, right? So this could be your cis 1, 2, or it could be your trans 1, 2. And frankly, this is as far as we're gonna get. When we get into chapter 5, this guy has yet another one, which is, it's an enantiomer. But we're not going there. Okay, so we're not going there. So again, the same thing. We have, for the 1, 2, you can have the cis 1, 2, and you can have the trans 1, 2. And for the 1, 3, you're kind of like in the same category. You can have your cis 1, 3, bless you, and your trans 1, 3. So if your multiple choice now are A, back again with a 2, okay, B would be 3, C would be 4, D would be 5, and then E would be 6, something like this, okay? I hope everybody understands that then these guys are not gonna count, right? You don't have to double them up, right? So, because people try to go for 7, you don't have to double it up. I mean, once you're calling it 1, 2, you're either gonna be cis or you're gonna be trans 1, 2. You're just not gonna be plain old 1, 2, right? This will be plain old 1, 2 if you're just doing constitutional isomers. So then the answer should be really the 5 that you're seeing there. And again, this will all kind of refine and be added more stuff in chapter 5. But right now, it should be then 5. Yes.
But if you do the one with the dichloro on the 1, 1, cis and trans, would it be 6?
You can't have cis and trans on 1, 1.
Oh, okay.
Yeah, 1, 1, you can't have cis and trans, so that's just 1. Amber. Okay, so for the 1, 1, you know, you can't, when you have two groups that are identical on a spot, you cannot have cis to you or trans to me. Right, so that's a very good question, actually. Okay, anybody else has any other questions with this? Okay, do you want me to start the discussion then for number, yes? People, you don't talk too much.
Yeah.
Okay, thank you. Thank you. I don't, oh, okay, wait. Actually, I probably am gonna need to borrow Are we full? We are full. All right, so we are full 15. So I'll keep switching us out. All right, so people should really look at the discussion packet to get yourselves ready, right, for the exam. The discussion packet is a good guideline of, you know, what a test would really look like maybe. So spend time with that. All right, oh shoot, I'm gonna need something else. All right, so here I am. All right, so the first question, and hopefully you have it in front of you, but the first question says, radical chlorination of pentane is a poor way to prepare 1-chloropentane, but radical chlorination of neopentane is a good way. I'm gonna go ahead and draw, and I'm gonna tell you exactly what this is saying. All right. So they're telling you this. They're saying when you are going to do a radical chlorination of pentane, so discussion 5, number 1, okay, and I go like this. They're saying when you're doing radical chlorination of pentane, and you put your light, and you do this, they're saying this is a poor way. This is poor way. And he says if you're doing a radical chlorination of neopentane, and neopentane is all of this, and they're talking about chlorine, and again, now they're saying that this is a very good way. Then how do we explain? So actually, all they want you to do is to explain. You know, why is this a poor and why is this a good way?
Is it
Go ahead.
is it because on the neopentane, the hydrogens are the same, like equivalent? So on the normal pentane, it's more random, so you have more isomers.
Okay, so I think what he's saying is totally right. I mean, if you look at neopentane, neopentane there are 1, 2, 3 hydrogens on there. There are 1, 2, 3 hydrogens on there. There are 1, 2, 3 hydrogens on here. And there are 1, 2, 3 hydrogens on there. There are 12 hydrogens that are called primary hydrogens. So the carbons are primary. There are 12 primary hydrogens here, okay? We already talked about that a primary intermediate, which will be these, are very unstable. But we have no other choice than to create a primary radical here. When I look at the example for the pentane, pentane also has primary hydrogens that are here, and it has 6 primary hydrogens, and they're all equivalent. But pentane happens to have other types of carbons with other types of hydrogens that would lead to a more stable intermediate. And the chlorination and the bromination of the pentanes or of the alkanes prefers the most stable intermediate. So when you're looking at your other option here, all of these hydrogens here, all of these blue ones are secondary hydrogens. So these guys are secondary hydrogens that are equivalent to each other, right? So these guys are secondary hydrogens that are equivalent to each other. And then we have these down here that are also secondary hydrogens that are equivalent to each other. In the chlorination of pentane, I will tell you that you will end up with a very low, about 2 to 3% of the 1-chloropentane. And it's going to be just based on, you know, the bond dissociation energy and the stability of the free radical. A secondary radical a secondary radical is a lot more stable than a primary radical. So if you have a compound that has selectivity, that's what you're gonna choose. So I think we have to really come up with a good answer to this. And if you say neopentane is good because you're taking primary radicals, I'm not gonna give you any points. Because the concept here is that they're primary here and they're primary there. So both of them are primary. So the real answer is, in neopentane, the 12 hydrogens are equivalent, and there's no other choice. I mean, that's your only way of making a halogenated compound, is to abstract one of those. While on the pentane, you had selectivity of primary versus secondary radical. Secondary radical the most stable, producing the most product. Yes?
So I'm gonna just see if I understand what you're talking about. So in reality, if you actually took chlorides and combined it with pentane, you'd most likely see it in the center there on that secondary hydrogen group. But since it's specifying that it's on the one, it's one chloropentane, you have an alternative option, which wouldn't be necessarily more stable if it was attached to the secondary hydrogens, but in this case it is because you have hydrogen, what is it? Equivalents around the whole thing, so you have like no other option, which makes it more stable. So
I don't think they're talking stability. Okay, so there's no, the question isn't stability. The question is, you know, would you be able to get one chloropentane from this reaction? Would you be able to get one chloropentane from that reaction? And the answer is, from the neopentane, you will make the one chloro. Okay, you will make that. From the pentane, you will not make the one chloro.
Because it's more likely to be on the secondary hydrogens in the middle, right?
Right, so what is important then is, it's not going to work, because you have options. And the option is really based on the type of carbon, the type of hydrogen, and the stability of that intermediate, okay? A secondary radical is more stable than a primary, so there is evidence, mathematical evidence, through calculations of bond dissociation energy, that is more favored, right? That the secondary is favored over the primary, and that will be the decision of you to go that way. You will not make one chloropentane, that will be noticeable. Did that help?
Yeah,
I mean, did that help? Does anybody else understand what we are saying? I mean, this question is critical for you to get right answers on an exam. You really are looking for the special type of hydrogen that you're gonna go after. I think it's a good idea to jump to the last question on that discussion packet so that I can really solidify this. So I'm gonna go to number 7 for a moment. I think it might be really, really good, and I know what I have to do, so I'll put it on there, okay? So if we continue with that same concept of it's good or if it's bad, you know, poor or not, if you're going to go ahead and look at ethane, and we continue with this, right? The question says, I don't know if you have it in front of you, but this is question now number 7. Question number 7 now says, despite the limitations of radical halogenation of hydrocarbons, what do they mean by that? Despite the limitations of radical halogenation of hydrocarbons, what is that in reference to? The limitations, what are the limitations? Well, if you have ethane, right, if this is your molecule of ethane, and you're gonna go ahead and do a free radical halogenation of this, back again with the chlorine, in presence of light, I mean, we know all the steps of the mechanism, right? We knew the steps of the mechanism. What are the steps of the mechanism for this? What are the steps of the mechanism? First thing you needed to do, you needed to cleave the chlorine molecule homolytically. Okay, that chlorine molecule homolytically just has now this chlorine radical that is quite reactive, and is going to go after the ethane molecule. It's gonna abstract the hydrogen, and it's going to produce now the ethyl radical. That ethyl radical can actually collide with another ethyl radical that could have been formed, right? So when you're looking at the limitations, this molecule of ethane, you could end up with 1 chloroethane, 2 chloroethane, 3 chloroethane. You could change all of those hydrogens, by the way. I mean, we're just saying, okay, we're gonna take one off. Well, that's not totally true. You can be taking more than one off. So that's what they mean by limitation. So we're like on paper saying, you're only going to remove one, right? Or you're going to remove two. It doesn't happen in real life, okay? That doesn't really happen in real life. So for the molecule of ethane, we just want to remove one and replace it with 1 chlorine. Would ethane be a likely candidate for this to occur? The answer is,
Yes.
I'm going to do a mono chlorination of ethane. Only 1 hydrogen will be replaced by 1 chlorine. Mono chlorination of ethane. Would this be a likely starting material?
Yeah.
The answer is yes.
Yeah.
The answer is yes. The reason being, if I remove just one, if you remove just one, and I'm coming over here to crazily draw this, and I'm gonna leave them just like that, and I put the chlorine here. Okay, the other ones are hydrogen, but I put the chlorine there. Would this be the same or different than if I go ahead and I put the chlorine here? The answer is they're the same, right? So when they are the same, that's how we started this concept of equivalent hydrogens. When a molecule has a set of all hydrogens that are equivalent, and you don't have a choice, right? There is no choice, then at that moment, this will be a good way of creating 1 chloroethane. We have no other way, right? So this is what we call, it's a good way, because there's no other way. I mean, if you, again, limitations, we don't know if you can only do one. We don't care. On paper, we can do just about anything we want. So with all that I'm going to control this on paper, this will be a good way. All the hydrogens are equivalent. But when they come here now and they're asking for the molecule of propane, okay, and the molecule of propane now looks this way, and you have all of your hydrogens on that molecule of propane, right? You have all of them, and they're asking the same thing. You know, would this be a likely compound that you can just go ahead and have one product? So they want, for which of the following compounds does radical halogenation just give a single mono halogenated compound? Would this be a good one? No, it wouldn't be. Because when you halogenate this one, your options are possible. You could have it in carbon number 1, possible carbon number 2. This is possible. Probable major product is not that. Okay, so again, you know, the difficulty of taking an organic chemistry exam is that you really, really have to read carefully. Okay, you must read carefully. If they're saying how many possible products, possible here are 2 products. It's everybody. That's possible. I mean, really, just about anything is possible. I am a true believer of this, just based on my life. So anything is possible. But if anything is possible, then this guy is not a good candidate for a mono halogenated compound. Not a good candidate, because you're going to have 2 options. Very different. Everybody okay with that statement? Everybody is okay with that? Very different than if somebody says, draw the major product of a monochlorination of propane. Right? If anybody says to you, draw the major product of a monochlorination of propane, then drawing this will be wrong, because this will be the major product of a chlorination. Yes?
When we're asked to draw the product of a chlorination, would you also want the HCl or only?
Well, for this time, I say yes, okay? For this time, I'm gonna say yes, because since we're just starting, it's a substitution and people really like to count. So I'm gonna say yes. Go ahead and say yes, yeah. Is everybody okay? She said, do you have to add the HCl? I'm gonna say yes. I'm gonna say yes. Like this problem would not be completed. So if we wanna finish the problem, you wanna come over here and then if we're gonna follow the structural view, right, if we continue writing the structural way, so we're gonna come over here, chlorine could be anywhere really, and then we're gonna add the HCl. Because if we have to do bond dissociation energies and it's not there, then it all collapses. I'm thinking in advance.
One last question.
Yeah.
Is there going to be, or you're not gonna tell, but, say you just say draw the products of propane, monochloro-propane.
Yeah.
Would you want all three of the possible, or the two possibles and then the, HCl, or?
Right, if they want all the possibles, then you have to draw everything, yeah. Okay, when we look at letter C, when we're looking now at letter C, finishing the same thing, they're saying, well, what about in the case of cyclohexane, right? What about in the case of cyclohexane? And cyclohexane is like that, and if you have to do the same thing, would this be a good, precursor? Well, yeah, because all 12, right, all 12 hydrogens in cyclohexane are equivalent, and you will end up with just one product, and that one product will be the chlorine in any one of those positions. And this name for this will be called what? What would this guy be called?
Chlorocyclohexane.
This guy will just be called chlorocyclohexane. Do not put the one in front. It is seen as wrong, because it doesn't matter where you're putting the chlorine, that will be your carbon number 1. Very different to the one above. The one above, if I say name that compound has to be 1 chloropropane. And the reason why it has to be 1 chloropropane is because you have the option. If you just say chloropropane, I'm going to ask you, what carbon do you want me to put the chloro on carbon 1 or carbon 2? If you have the doubt on the question, then you have to include the number 1, right? So if you say this is chloropropane, I'm going to say, well, where do I put the chloro, right? And if I have to ask, then your name is incorrect, okay? Over here, if you say 1 chloropropane, it's like, really? Really? I'm going to put it on carbon number 1. The story totally changes if you have more than 1. If you have more than 1, even if you put them both on carbon 1, right, even if you put them both on carbon 1, you've got to tell me that they're on 1,1 dichlorocyclohexane. Is everybody? Because if you don't tell me 1,1, again I'm going to ask you, well, where do you want me to put the chloros? Do you want me on 1,1, on 1,2, on 1,3, on 1,4? Right? Because those are all the options with the cyclohexane. Positionals, 1,1, 1,2, 1,3, 1,4. So if the question exists, the numbers are real. That's why the numbers are there. The numbers would be there so we don't have to have a follow-up question so we know what to do, okay? All right, when we look at letter D now says, and I want everybody to do this if you haven't done so. Letter D says I have, and I'm going to be quiet, 2,2-dimethylbutane. So they're asking for 2,2-dimethylbutane, and they want to know, would this be a good choice? Well, of course you're going to say this is not a good choice. This is not looking symmetrical. Well, that's probably not what I'm going to ask, So how many possible monohalogenated compounds would you get from here? How many, I didn't leave my say of room above, so how many possible monochloro compounds from there, from the one above? Okay, so how many monochloro compounds from, bless you, the 2,2-dimethyl? Anybody? He's telling me 4. Everybody agreeing on that? They're saying 4. Not 4? Okay, so we have 2, 3, 4, 5. 2, 3, 4, 5. How many people say 4? Raise your hand. And people that are saying 4. Okay, people that are saying 3, raise your hand. People that are saying 2, raise your hand. Okay, so I think what we need to do is the what if, okay? You really, every single time you go to the what if scenario. And the what if scenario is hypothetical, right? It's hypothetical. I'm gonna go to the line angle and tell me if this destroys your spine. But I'm going to the line angle to make life a little easier. Yes, may I? And this is what I mean by line angle. My line angle is gonna look like this. I have in carbon 2, I have 2,2-dimethyl butane, right? So if I put the chloro here, and I'm making the easy ones first, if I put the chloro there, it's gonna be very different than if I put the chloro here. Yes or no? Okay, if we have to name this guy, if we're naming this guy, the name is 1-chloro 2,2-dimethyl butane. If you're naming this guy, it's gonna be 3-chloro 2,2-dimethyl butane. Okay, if we name this guy, okay, if we name this guy is 1-chloro 2,2-dimethyl butane. If we name this guy, numbers are first. Numbers are first. So 223 is lower than 233. Everybody? Okay, because you know, in the back of your head you want to put the alphabet. The alphabet is after. The alphabet is after. So your choices of coming from this side or that. So you come from this one, this will be 223. If you start from over this side, it will be 233. That's not as good. So 223 is lower than you would start with 3-chloro 2,2-dimethyl butane. So they're different. If you come over here and you draw this one back here and you keep that, the chloro is here. The chloro is here. And so now you would start here with 1-chloro 3,3-dimethyl butane. If you have a substituent on carbon 1, you must start from there. Okay? All right. So these are the easy 3. These are the easy 3. All right. But many of you, when you see 4, perhaps you're looking at these positions, right? And if you're looking at those positions for the people that said 4, if you're looking at those positions, go back to that, right? And so let's say I put the chloro on this one, right? So you're putting the chloro on that one. Is that different or the same as any one of them? Not everybody can see it. Everybody, not everybody can see it. So don't beat yourself in the plaza if you don't see it. What is a good idea is to use your naming. Use your naming again. If I'm naming this one, this is going to be 1-chloro, right? Now the longest chain is going to be this way, right? The longest chain is going to be now this way. And that will be 1-chloro 2,2-dimethyl butane, just like that one was. So there really are only 3 possible products for this compound. 3 possible. Is everybody okay? Is there a major and a minor product here? Is everybody okay? I see people, is everybody understanding, the students that had 1 or 2 or something? And the thought process, right? So what we want to make sure, I mean, I'm really big into having a process that you're going to put in your head that you're going to follow, all right? Because, you know, usually the test, we put another example, you know, and you have to have that thinking ability of how to rationalize what you're looking for, right? So we're looking for that aspect here. So we got it, there's three possible, right? But now the question is there a major product in here?
The secondary.
And everybody can see that, yeah, the only major here would have to be this one. Because the ones at the ends, these guys are primary and these guys are primaries, which will be exactly the same. It doesn't matter if you're on position number 1 here or you are in position number 1 there. Remember, the concept is not stable. The concept is the most stable intermediate. Okay, and the most stable intermediate is the one that would have the most substituted free radical. A tertiary radical is more stable than a secondary. So if you were to be able to come up with a tertiary, that's your major product, okay? All right, then we look at the next one, which is methyl cyclobutane. When I look at methyl cyclobutane, so back again with the same story, this is cyclobutane, and that is methyl attached to there. Well, I mean, obviously, if somebody's asking you, is this a good way for a monohalogenation, I hope that you immediately say, well, of course not, right? Of course not. It's not a good way. There's no symmetry here. There's a lot of different types of carbons here. How many different types of carbons do you have in methyl cyclohexane?
3.
There are 3 different types of carbons, yes?
Yep.
You've got your primary over here, right? You've got your secondaries all over here. These guys are all secondaries. And then this guy in the center is your tertiary. So you have primary hydrogens. There are 3 primary hydrogens. There are 6 secondary hydrogens. And there's really only 1 tertiary hydrogen, right? So not a good way. Now here's the crazy story. I mean, if I really was totally evil, which of course I really am not totally evil, how many possible mono, bromo, methyl cyclobutanes are there? Mono, bromos, how many? 4. They're telling me 4 right away. Is that true? People, there's 4 screamed at me, yes or no? Yeah?
I think.
I feel like because the computer is on that side, I just kind of hear that side. Yes, how many? 3, 4, 5? Any idea? 3? Okay. 4, 5, 3?
4.
Okay, everybody in 4?
Yeah.
3? Okay, it's a good idea to just look at the positions, right? So, yes, there's gonna be 1 when you put 1 there. And I think everybody may have seen that. So that will be 1 if you put that 1 there. Very unlikely, by the way. That's the primary, but possible. Possible. We're not asking major. It's very possible that you could have removed that tertiary and put it there. So these 2 should be like really easy to see. The people that are saying 4 are students that immediately recognize that even though these guys are all secondary carbons with secondary hydrogens, that these 4 here are equivalent. Those students saw that these 4 were equivalent, and it didn't matter which one you took away or replaced, you were going to end up with the same product. You were going to end up with the CH3 here and a Br there. And that would have been the same as the Br here. They would have been in a 1-2 positions, right? But then there were students that immediately also recognized that these 2 hydrogens up here even though they were secondary, they are actually equivalent to themselves, right? So they were equivalent to themselves, and the replacement of any one of those two will produce yet another compound like that. So the people that said 4, you're correct. The people, that would have said 5, it's probably correct, because you can have cis and trans from here and cis and trans from there, but, we're trying to stay away from adding too many layers right now. So right now, 4 is the correct answer, because we're looking at positionals, we went to the, the free radical went after the number 2 and the number 3. Yes? If they ask you to draw the major monobromination of this compound, okay, I hope everybody goes ahead and just gonna go ahead and draw that as your major monobromination and doesn't do anything else, because that will be it. All right? Okay, we're backtracking, and I'm just gonna go ahead and go to number 6, and now we're going the other way. When I'm looking at number 6, they're saying label each hydrogen as primary, secondary, or tertiary. So I'm gonna go ahead, and the structure in the book, in your paper, is like this. And the reason why I put this there like so is because I wanna make sure that you understand that the test is yours. Okay, when you're taking that test belongs to you, and you convert anything on that test to something that is comfortable to you. This is not comfortable to me at all, okay? I don't think I could do very well with this. I think many of you are probably gonna feel very comfortable trying to convert this to this, okay? And if you feel very comfortable taking your CH3 that is there, well, you should be able to, how's that? Maybe I'm not saying this emphatically enough. You are expected to be able to take a condensed structure, convert it to a structural structure. You should be able to also convert this to a line angle drawing, right? So that movement from one to the other is expected of you. Yes? Hi?
No.
All right, so when they're asking you for primaries, hydrogen, they're referring to the type of carbon that that hydrogen is bonded to. So if I am bonded to a carbon, and that carbon is only bonded to one other carbon, these blue carbons are called primary. All of them that are blue here are primaries. That one, and that one, and that one. They're all primary carbons. Primary carbons will have anything that is on it will be referred the exact same way. So since you have 3 primary hydrogens, all those 9 hydrogens are also called primary hydrogens, okay? The carbon here in the center is a carbon that is bonded to 1 and to 2. That red carbon there is called a secondary carbon. Those hydrogens then are labeled the same way. They will be called secondary hydrogens as well. And the very last one here, which is this carbon, and this carbon is bonded to 1, to 2, to 3. That carbon that is bonded to 3 is then called a tertiary carbon. That hydrogen then is labeled the same. It will be labeled as a tertiary hydrogen. Okay? And I don't think people have troubles with this, but when we start alkyl halides, I'm not talking about this, I'm just mentioning the type of halides that you have. So this skill is for now, and then we move on. So for letter B, again, when they're doing this and they're saying CH3, 3, C, CH2, CH3, I very quickly convert this into my line angle drawing. You should be able to convert this to a line angle drawing as well, okay? And I'm seeing that I have that is what I have. I have 1 CH3, 2 and 3, and then I have a CH2 and a CH3. So the going from here to the line angle, again, is expected of you. All right, I'm expecting you to be able to go from this to a line angle. And yes, that is gonna be on the test somewhere, you know. I mean, you're expected to know how to do this. What question on the test it is, I have no clue, but I mean, you're expected to know this. All right, and then immediately, well, we see that there's only 2 types of carbons here that have hydrogens on it. There are 3 different types of carbon, it's everybody, but that's not the question. The question is asking, label the hydrogens. So, if we're labeling the hydrogens, there's really only 2 types of hydrogens. There are all these guys out here that are primaries, these blue dots. They're all primary hydrogens, all of them are primary hydrogens. And then the red dot here, it's a secondary carbon and a secondary hydrogens on it. There is a third type of carbon, that wasn't the question. So we're adding another layer. There's a third type of carbon, and the third type of carbon is that guy here, which is called a quaternary carbon, which, by the way, they don't really are reactive, they're totally saturated, you know, but they're there. We call them quaternary. Not tetra, these guys are quaternary, from quattro, quaternary. And quaternary is just, you have 4 attachments on that. I don't even think we have to do the methyl cyclopentane, but I'll do it anyway. So methyl cyclopentane that looks like this on your paper, you cannot do a condensed formula for this. This is it. Okay, so I mean, don't spread this out in all the chapters, this is it. You cannot break this down. So how many types of hydrogens do you have in here? Is everybody seeing 3 different types of hydrogens? 3, your primary, your tertiary, and then all the secondaries, right? All the red dots have secondary hydrogens on it. So all those are secondary carbons, secondary hydrogens. Okay, I'm going back to number 2 now. I'm going up to number 2. And they want you to go ahead and calculate the delta H. And the calculating delta H is really saying this, okay? Calculate delta H, and I think I write this on exams now, is really calculate the bond dissociation energy. That's really what we're looking at. The bond dissociation energy is seen kind of like the enthalpy for the reaction. And in your packet, we have this. I'm copying what I have in here, all right? And I want you to really take a look and see exactly what it is that you're breaking and attaching. Because when you're looking on the tables, right, if we give you tables, you really, really need to know what exactly it is that we're doing. So do you see what bonds are we breaking? Are you seeing the bonds that we're breaking? I think this one's easy. I know I'm gonna be breaking this one. I know I'm gonna do that. When I look over here, which one I'm breaking? It looks like I'm breaking this one, right? It looks like you're breaking that one. And then when you come over here, it looks like I'm forming this one. So this is the bond that is being formed right there. And when you're looking over here at the CH3I, it also looks like you're forming that bond right there. Okay? So your table that is this, that could be given to you on an exam, that's table 4.2 in your book. That table did not have the energy necessary to do this. So this was given. This is 335, and then is there a question? 297, yes or no?
Yeah.
Yes, go ahead, what is the question?
Oh, no, I was just confused.
This is?
I was just confused with the number.
Oh,
I
okay, yeah.
thought you meant.
Yeah, and then the CH3I, so it's really important that you know what you're looking for, right? So that CH3I is the bond formed between a methyl and the iodide, right? It's the methyl and the iodide, and that's 234. So I'll put the 234 here. So this bond dissociation energy, I don't know what it is. Did anybody calculate it ahead of time?
I got a positive number.
Positive? Okay. You got it positive?
Positive, yeah.
50?
I know I didn't use the weight table, so my number's a little off.
Okay, and your number came out to be what?
My total would be 11,
Okay.
positive.
And your total, you used
Yeah.
this table. Okay, and you came out 50, okay. So plus 50, and this is kilojoules per mole. So a plus 50, that is a kilojoule per mole, is saying that the reaction is, what are we gonna say? It's endothermic. You're gonna say that the reaction is endothermic. And this is the stretch, that we use. The stretch that we're using is that delta G equals delta H minus T delta S, right? Remember that? I mean, everybody knows that one. And when you're looking at a delta G and the delta H is a positive number, the component of temperature and entropy, the majority of this, the entropy component is not gonna be significant because most of these things are done, I think, in the gas phase. I think this is all done in the gas phase. It doesn't say, huh? Well, we don't see that the entropy contribution is big, so something that has a positive number, we're also saying that this is possibly gonna be a delta G that is positive, and it's not spontaneous. This will not be a spontaneous reaction. This reaction we will never do in the lab, because we would have to supply huge amounts of heat, huge amounts of time, things that we have none of that in a lab. Okay, so that's what that is saying. When you're doing the next one, right, which is letter B, this time we're asking you to use the entire table. So when you're looking at it, we really are asking you to be able to figure the table yourselves. And I don't think that's gonna be very difficult after you've taken a whole semester of, Chem 2, that you did a lot of tables in Chem 2. Right? So, what I know that what I'm doing here, and again, if you have a difficulty, you make this problem yours, right? You make this problem yours. It's obvious that this is a tertiary carbon-hydrogen bond that you're breaking. This table is very nice. Perhaps my table is not gonna look like this, okay? So be ready for, whatever table I can pirate from Google might not necessarily be this one, because all the tables that I get from Wade, I cannot chop and do with it whatever I want. Is everybody clear? So perhaps don't be, if the table doesn't look like this, don't jump off the bridge. But, you're looking at breaking a tertiary like that. That's what you're looking to do. So that will be the number that you really are looking for in here. All right, so that will be your 381. So you're doing a 381 and breaking a bromine-bromine bond was 192. And then generating a carbon-bromine bond tertiary was 272. And then your HBr, which is 368. And now again, when we're doing all of our numbers, did anybody come up with this too?
A negative.
Negative? 67? Ariane, you got the same number?
Yes.
Okay, negative 67, yes.
For the first one that we did, I didn't, get, plus 50. When I added them up together, I got 632 minus 617, which gave me 15.
so let me do this one. You got those same exact numbers?
Mhm.
Okay, so 335 plus 297. This is here, whoops, 632. And then 383 plus 234. This is 617. Well, if we use these numbers, your number is gonna be right. Yeah, so I get 15 also. Let's see if I was the one that made a mistake with the HI. My HI was 297, and the CH3I is 234. I get the same number as you. So I got 15 plus 15. We did get plus 15. I mean, if these numbers are correct, like I know I'm doing them correct. Did I make any mistake? 335. Okay, so the number is coming out to be, the BBE is still positive, but it's plus 15 kilojoules. That's what you got from another table.
Yeah, but I got 11. So I used a different, so the numbers are slightly,
You did a different table and you came up with what?
11.
11. How did we come up with 50?
Did you just misheard her?
I heard them wrong?
Yeah.
Ah, I heard them wrong.
I was saying 50.
I'll get new hearing aids. Maybe these ones are not working. Let's take them. All right, sorry, it says plus 15. All right, plus 15. You know, Californians speak a little differently than I do. Like, oh, Josh. Half the time I'm having a difficulty. All right, so the next one, number 3, they want you to go ahead and sketch. I'm assuming that everybody had that one right. Yeah, go ahead.
When it says, or on this one, it doesn't say to label it, but on number 4, it says to label everything. I know you want the transition state and the axes and the products and reactants, but would you also want the enthalpy and the activation energy?
Probably, yeah, when we want to label everything, did you draw yours?
Yes.
Okay. Did anybody draw these sketches? Anybody that is a good artist? Yes? No one is a good artist? Or nobody, or no one has done it? What is the story? I wanna know, huh?
Not that.
Are you a great artist?
I don't know about that, but.
You don't know about that? But at least it's drawn, huh? All right. He says, well, I don't know about that, but at least he's got it all drawn. So I'm gonna go ahead and maximize it a little more. I absolutely love this thing. So for number 3, they say, sketch an energy diagram for a one step that is very fast, la 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 la, and highly exothermic. So I see all that perfectly in that drawing. I mean, I can see that, I don't have pencils on. I see that that is gonna be very fast. For me, very fast means what? That you have, right, so very fast means a low, small energy of activation. So you need to have for fast, it's going to be a low energy of activation, okay, or small, that low is my stove. Okay, so small energy of activation. And you can figure that out, by looking at the energy of the reactant, and that energy of the reactant has to be really, really close to the energy at the transition state. So you want the difference here to be very, very small. You want those two heights to be very close to one another, to be very, very fast. And then to be highly exothermic, you want this distance actually, so this distance, which we really are looking at the delta H here, to be really, really significantly different, right? So you want that change to be very different. Sorry to be writing on your paper.
It's fine.
That's why I look for the
For the
pencils.
transition state, can we just do the through,
Yeah.
or do you want us to label changes?
No, for the transition state, you didn't have to write it. All you could do was that guy, which is the not equal sign, that's what I call it. It is not equal, is that little sign, and that would have been enough. So for the second one, I wasn't really specific, right? So the only thing that I really said to do was that it was it was a two-step, so that is the two-step. And we wanted the first step to be endothermic. So endothermic is the difference between the energy of the reactants to the energy of the intermediate. And you needed to have the energy of the reactants be lower than the energy of the intermediate, so that is correct. And then I said for the second step to be an exothermic second step, so it is to here to there. He's come up with an overall exothermic reaction. Yours didn't have to be overall exothermic. Is everybody there? Because I didn't say that. So if you had to draw something and everybody talks about the test, and you all confer that you're both wrong, okay, the answer is that you both could have been right. I'm not specific enough, right? So I'm not specific enough. I would be saying that I'm missing stuff here, right? So if we said label everything, this is not labeling everything, right? So we would like to have the reactants written there, right? And we would like to have the products written here. That's what we mean by labeling everything. We would have the first transition state 1, the second transition state 2, right? It would be nice that you label the energy of activation, right? So this is the energy of activation here, and that will be the energy of activation here, right? So that's labeling everything. So if you have to label everything, perhaps this is why we need so many pages on a test, because I would like this blown out so we can all see it, right? So you wanna be able to write in your own table, if this was a test question, right? If this was a test question. But this is perfect, this is perfect. Okay, for the last one in the discussion packet, which is using the bond dissociation energies from table 4.2, propose a mechanism for the radical bromination of ethane. So you really are starting out, I'm gonna borrow your paper.
Go for
It's just too handy. It's too handy.
I didn't finish all 5 though, but
You didn't finish it all, don't worry about it. Okay, well, I'm gonna write something differently, just for a moment. When they're asking you to propose the mechanism for the free radical, it might be a good idea, that you begin like this. This is ethane, so you start out like that, and you're doing the bromine. You're gonna add light and heat, sometimes you really do need heat, and you have that there. Like so, and that will be, the reaction. So I'll say it differently. I am expecting you to know that if I say the bromination of ethane, that you should be able to come up with a product, okay? That's part of this test. Okay, that is part of this test. Leaving the HBr off might be a problem when you have to calculate the bond dissociation energy. Kylie? And I think that's the only reason to include it there, is to make sure that you know that it's needed so that you have the right answer. Did anybody calculate that? Anybody calculated that? Negative? 5.1? Okay, so the BDE here is gonna be negative 5.1 kilojoules per mole. And that's you using the table. You're breaking these, breaking that, you're forming this, forming that, and you got the numbers from the table, okay? If they want you to propose a mechanism, that's different than this, right? This is just, they're coming up with the answer. Proposing a mechanism, you are having to, I'm gonna use his paper because that way I can do things, okay, like for example, he's doing this, the initiation step, and actually that is not a correct initiation step. The initiation step begins right here. Okay, so that is the beginning of the initiation step. In the initiation step, what you're doing is you're cleaving the halogen homolytically, okay? And that halogen homolytically, you really need to show the arrows. So, in doing so, you would be able to do that, and this guy moves there, and then you end up with your two BRs, and then that's, and again, I mean, I don't know if I'm gonna have you do this because this is time consuming and kind of silly, but in the propagation steps, they look very, very good. You already have the reactive species, which is the bromine radical. The bromine radical is going to go after a hydrogen, generating the ethyl radical and HBr. And then the ethyl radical goes after a bromine. Now you didn't need the light there, it's everybody. So the light is just to start. And that's why it's called a chain reaction, because even if not all the bromines were cleaved at the beginning, if there's anything left over, I still can cleave it. And so that was that whole concept, you still can go ahead and cleave it. And you really want to show in your propagation steps, you really, really want to show the formation of your two products that you said at the beginning. So you need to show those. And then the very end, which are the famous termination steps, where you are, he went a little quick at the end. Usually a termination step, you really want to go ahead and show, that the ethyl radical, like he did here, so you really want to show that the ethyl radical is going to hit the wall, and then you end up with the product of the ethyl with the wall. So they want to see the radical before, because he just wrote the product, because everybody, that is not the reaction. So if they want the steps of the mechanism, that will not be the reaction, that would just be the product of a termination. So all he did was write possible products of a termination, not the reaction of the termination. Is everybody seeing what I mean? No? Okay, so another one here. To show that product, it should have been shown like this, that ethyl radical is going to collide with this ethyl radical. These two are going to collide, and they're going to end up forming the butane compound. So that would be the reaction.
So you have to show the whole thing.
Well, yes, if
Yeah,
they
you
want
have
the
to.
mechanism, then you have to show the whole thing.
Okay.
And then you would, huh?
That's for what part of complication?
This is a termination step.
The one you wrote in pencil above it?
They're termination steps, right? When you really are now done, there's no, you know it's a termination step when there are no radicals as a product. That's how you know it's a termination step. So you cannot have radicals for products. Okay, believe it or not, we've used the whole entire time. What the heck? But we managed not to put it